Let's continue on with taking a look at the Nillion examples to get more familiar with the Nada language. So I'll just start up that Python virtual environment. Actually, it's source and activate. And then I'll open up the example repo. We're going through the circuit simple example here. On the left side, we have the Python file. In the middle, we have the Nada program. And pretty straightforward for the Nada program. What's happening is we have the single party being set up. The name is party1. And then we have 4 integers, secret integer inputs, all belonging to party1. The output will be this line here. The new integer 3, it's given the my output name, and it's accessed by party1. So we can see here on the Python program, the first part will be setting up the Nillion network, which reminds me I need to then start the program by running this bootstrap local. So let me just run this command here. And once this is running, then I should see in my task manager or the activity monitor, the Nillion devnet process. All right. So that's running. And then let's go ahead and circuit simple. And it gives us 22 as the value as expected. Again, it's basically storing the program. So we're just getting our network, loaded into this program. It's already running. We're just getting the cluster, and then here's where, we're storing the program. And then we're storing the secrets. We're binding the secret integers, and then you're using the store, and then we're doing the compute and bindings, and then here's the compute time secrets. So this is 12. This is new int 1. This stored secret here will be new int 1. So that's 12. The compute time is going to be new int 2. That's 10. And then here's the compute. All right, let's get into coding. I've already created a repo for the ETH Global Hackathon. What I'm going to do is I'm just going to clone the Nillion Python starter and just start to create the program from there, just using how their repo has things set up where their program folders, and so that's what I plan to do. And once I get what I'm trying to envision as a demo, I can probably move over to the ETH scaffold and create something there for a final demo. But let's go ahead and get started. So I feel like I want to just remove all this unnecessary programs here. Just so that it's a lot cleaner. Looks like I can create my own folder. Maybe I'll do that as well. Yeah, probably do this. I'll follow how they have like their mini compute programs. Maybe I'll follow this type of example. Okay, so let's go over this Python sample program that I just created. I took this data set that was found and I just converted and saved it into this data folder in a CSV format. And we can take a look at that data here. It's actually open. But what we can see is on the last column is the target value, the diagnosis value, and in the dataset file, the diagnosis is either a malignant M or B for benign. And what I first did in this program was convert using the this line here, the lambda, to basically change the value of an M to a 1, and else it'll be a 0. So 1 will be malignant, closer to 0 will be benign. And the next lines is just printing the first 50 rows of the data. I just did that primarily to make sure that this code here works. And then in the data set, I'm dropping the ID column. Pretty much, we only care with what, the attributes that we're going to use. So that's being taken out. And then on the next set of the code, I'm basically creating my train data set. And the first part here, I'm basically taking 80% of what would be the size length of my data set that I feed into this. And that will be my normal training data. And then the rest will be used for my test data that I'll randomly select a row in that test data to act as like the patient. And I also created a subset data, which in this case is just 25% of the 80% of that data set. And it's just for here to create a healthcare provider that might have a lesser data set than a full, just to produce varying prediction values, because that's the whole point of wanting to potentially create an infrastructure where you can do blind computation, so that we can work towards a healthcare infrastructure where all healthcare providers that will contribute all the data set values that they have, and potentially they can do it in a way that they don't have to actually reveal, but they can combine for the purpose of just running some computations. So in the next set of the program, I'm basically running some plots. The first frame will show the distribution plots of each of the attribution data in the data set. That's the 80%, the full data set. And then there will be another frame showing the distribution plots of the smaller data set. And then from there, we're basically removing the diagnosis column. Then a random row is selected just to make a case for some patient data. So in the full data set, we have 80% that's being used for training, and then the other 20 is just going to be some test data. And in this case, it would just be selecting one from that 20% at random. And then part of doing the classification models, we need to add the MP1s, or we need to add the ones column to the data. So that's what this NumPy will do, this line here. And we're doing that for both the normal data set and the subset. And then from there, we're able to from there, we're able then to create or calculate our coefficients, the thetas. So we have the two thetas there, and we can print out those just so you can see the difference will be small, but in the calculation, the final calculation of things, small differences does show up in the final prediction values. So from there, then we add we add the ones column also to the test data. And then we do our calculation, basically doing a multiplication of the augment and the theta. And then we get our prediction values. The final set of data here, it's pretty much a repeat of this code here. And the only reason I have it here is because when it comes time to creating the Nada program, I need to do it in the way where I'm not using libraries. Basically, I'm just needing to do normal, operating, using normal operators, which, we're able to use these built-in operations from the Nillion, the Nada language. So that's the reason for this here. I'm just making sure that I can get the correct code to produce the same prediction as the full data set here. So let's go ahead and just give it a run and it'll make more sense. So after running the program, the first set of data distribution plots that we see is with the full data set, or what I consider the 80% of the trained data. And, we can see the distribution of the diagnosis here, the frequency, it's at hundreds of values. So we know that, we're seeing about 80% of the 500 something instances in our cancer data file. And the next plot of the data, what we'll see here is the subset, the 25%, the smaller data set that will be used. And then let's take a look at what was printed out here. So when we ran the file, again, I just have a printout of the first 50 rows of data. The main purpose of that is to make sure that the conversion of the M was to the numerical 1 and the B to 0 was happening. And then we can see here what the randomly selected image instance. So this was in the cancer data set file. Row 479 was selected. And we know that, we'll probably get close to a value of 1, in the calculation. So as we continue on in the program, we can see that the coefficients was ran in both the full data set and the subset. If we take a look at the prediction values, we can see a small difference in the prediction value. So what I plan to do in the Nada program is I think I'll take the coefficients that's produced from, all these computations prior in the code. Then I'll use these as the secret inputs into the Nada program. And in the computation, we can run this set of code here in the Nada file, which is, basically doing the multiplication part in here. What I think I'll have is the party 1 input will be the X test values, will be the vector. And then the other parties would be, these coefficients. So we'll see how it goes, but that's the plan for the next step in this Nillion healthcare program project.